Good, thank you. And thank you everyone in the YT community. Well, thanks Stephanie and everyone for organizing this meeting. It's been really neat hearing about a lot of different research, but also just thank you everyone in the YT community for really building a stimulating community where everyone's really like helpful and very nice about things. So I'm going to talk about some different sort of issues I've had with YT and how I've overcome them. And even more so than sort of overcoming issues with YT, or actually really more MPI4 Python. More so than that, it's really uh, allowed me to develop sort of a analysis framework that I'm applying to different analysis that isn't even primarily in YT. I'm going to start with just talking a little bit about some of my successes or some pretty plots that I made using YT before I had to deal with parallel YT, and then sort of the motivation of there's never enough time, it seems like, and why to do parallel, and then how I overcome some hurdles and show another round of pretty plots at the end. Okay, so first of all, so this is going to be a pretty informal talk, by the way. Definitely, Mike gave a really awesome talk, and my talk is going to be a lot more informal. So, just going to give the very briefest of introductions on kind of my research. So, we're looking at some of nature's prettiest pictures, in my opinion. Here, on the left, we have a starbursting galaxy. So if you just looked with an optical telescope in someone's backyard, you'd see just the white material here. It's the galactic disk. And then if you look with Hubble Space Telescope or something, you see all this red filamentary material, gas flowing out of the galaxy at a few thousand kilometers per second. And then on the right here, we see, again, some optical material in the whitish blue or yellow colors. And then in the red is some neutral hydrogen gas, which is being stripped as this galaxy plunges into a galaxy cluster. And so this is, so everything I'm doing these days is with a focus for being easily transportable. So this is the downside about Google Slides I found is it's a bit difficult to synchronize movies. But this is some pretty projection plots using showing the magnetic field as quivers or as arrows. And on the left, we have a run without any cosmic rays. In the middle, we have a run where cosmic rays advect along with the flow. And on the right, we have a case where cosmic rays diffuse. And if you look at the very end of the movie, you can see that they have rather different looking morphologies in the disk. But so what are cosmic rays? Let's see if I can get this to the next slide. Oh. So what are cosmic rays? Cosmic rays are these really high energy particles. And a fun fact is that a single cosmic ray proton, if it were to hit you and deliver all of its momentum to your body, you'd feel the same force as 100 mph served by Serena Williams. So thankfully, cosmic rays don't typically directly interact with us, or we'd be constantly buffeted around. Let's see if I can go backwards. There we go. And another success with zero YT is looking, again, with cosmic rays with different transport, whether they're advected, diffused, or have some temperature-dependent transport. And this is sort of a zoom in of the galactic disk that I was showing before, looking edge on, and you see very different wind profiles generated. And so just briefly, different fluid transport processes in case you're not familiar with them. So for advection, you have something where it's simply tied to the gas motion. So we have these moose, which are advecting on the ice blocks along the river. They're pretty much just doing what the river feels like doing. Actually, moose, or this might be elk, in fact, are very proficient swimmers. So I've been told that they should be able to make it out of here okay. You have diffusion. So this is showing a hydrothermal plume at the bottom of one of Earth's oceans, and you see that kind of like in Mike's talk, you have something where it's really spreading out as it goes, as it's buoyantly rising. And then for temperature dependent transport, I won't go into the nitty gritty plasma physics, but essentially cosmic rays travel much faster in cold regions and are braked in warmer regions. And so this is a lot of what I do, honestly, is post-processing with YT and then using Matplotlib to do different visualization work. I do really like YT for projection and slice plots and getting into phase plots a little bit. And then this is doing a time series analysis showing, again, in the different transport cases, you have very different outputs. But let's focus a little bit more on what I've been doing more recently. So the issue with one of my more recent projects is that it's no longer the case that I have roughly 3 simulations with a few hundred files. Instead, I have roughly 1 gigabyte files. I have about 1,000 of them, a bit more than 1,000. And I'm doing a parameter study, so I have around 100 simulations. Probably somewhere between 50 and 75 right now, but probably have 100 by the time it's done. And so this is rather a lot of data. I can't copy it onto my local desktop anymore, sadly. I have to do the analysis on the cluster, and doing it in parallel is essential for getting it done in a tractable amount of time. And so there are a couple of issues that I found, and thankfully the YT community is very actively updating YT. And so quite a few of my issues have just been fixed by going to more recent YT versions. More recently, I had an issue where it's kind of strange. My script was able to work for less than 50 files. And I found that that had to do with one parallel loop. But when I tried to do a second iteration of that loop, there'd be a MPI4PY buffer issue. So that was kind of annoying, but on the plus side, I found a way to automate my whole analysis, whereas previously I was doing everything not really by hand, but I really found a nicer way to set up my whole analysis framework, which I thought I'd share with you all. So the very first step is just having some job which runs forever, submits a analysis Slurm file so that I'm not doing any work on the login nodes. So this submits another script, and then that script calls this analysis driver, which calls a bunch of different Python scripts that I wrote, and does 2 loops over directories just based on how I have things set up. And then the meat of what happens is in this other Python file. So the main YT related thing that happens here, I'm basically just taking my HDF5 files, which were run in Flash, and transforming that into much easier to manage NumPy arrays. And so this is the parallel part. And I'm kind of wondering, so this is part of the reason why I was interested in giving this talk, is also just interacting with people. And I'm sure there are better ways of doing different things. So I like working with NumPy arrays, whereas although I do know that in Python, dictionaries are supposed to be the nicer thing. So the parallel loop works with this dictionary storage. And then what I end up doing is I unpack that. Let's see, I do this loop and unpack all that dictionary storage. The reason why I do that is I think kind of necessarily all this stuff is out of time order, and I like to sort it in time order. And it's just easier for me to think about too. So probably there's a better way for me to do this. And then I just save all the information. I have this set up where the analysis driver does 1 loop over, basically it says just loop through 48 files or the number of processors, and then we'll do this iteratively. And as a result, we have some pretty visualizations where on the left, we have a slice plot where initially there's this cold, dense cloud and a hot wind. So kind of what Stephanie was talking about, but in a much more idealized setup. And we're seeing that there's survival of that dense material in this very cold, dark 10 to the 3 Kelvin gas, which is the initial temperature we started out. But then there's also this substantial mixed phase at around 10 to the 4 Kelvin. And then on the right, I'm showing in red, blue, and green a couple different cloud temperatures, showing that we have mass growth over time on the top. We have the shear velocity between the wind and the cloud drop off close to zero pretty quickly. And then we're also including dust particles in these simulations and looking at the ability of those dust particles to stay in the cold gas throughout time. And then the left versus right is just showing, again, one parameter, the overdensity between the cloud and the hot gas initially. So just showing some different simulations. So moving on. So one thing I'm really excited to do is play around with volume rendering. So thanks to Matt for posting RHytIDV. I realized that there's been volume rendering in YT for quite a while, but I was really used to using visits sort of widget to just do volume rendering pretty easily. So I'm really looking forward to checking this out. And then I already mentioned there's probably a better way to do this. And then I was also reflecting, actually, just before giving this talk, I realized that the MPI4 issue might have to do with it being sharing all the data to all the processors, whereas when each processor has the individual data, it seems to fit within memory. So one thing for me to look into is to see if I can modify that and try to see if I can just collect data on the root node in a broadcast or in a point-to-point communication rather than broadcasting to all the processors. And so thanks, that's the end of this presentation, and ready for questions or comments or suggestions, really anything that people want to talk about.
Awesome. Thank you, Ryan. So I see 2 hands immediately went up. I didn't see which one went first, so I'll go with Josh because Corentin got to ask a question before.
Thanks. Thanks for the talk, Ryan. I just got a question about your Slurm submission.
Oh yeah.
Thing. Can you go through that again? I don't really understand what's going on here.
Yeah. So this is a pretty short file where so I have to execute this with I think this is called auto analyzer. So on the login node, I'll have one terminal which I don't like to background things because otherwise I forget about them. So I just have one terminal which has this executing, and then I'll know if it stopped as well. And just every 2 hours, it'll check. So the result thing is checking whether my analysis script is currently in queue or executing. And if it doesn't find it, then it'll submit this analysis.slurm script. And then do you have a follow-up question related to that?
Yeah, I was just wondering why you kind of do it this way instead of, say, I don't know, you could have the simulation code put out a Slurm SBatch to analyze the snapshots it just dumped.
Yeah, that's a good point. So I originally was doing something similar to that, where I had a dependent job where as soon as the simulation was done, it would do some analysis. But the nice thing about this is I can take a look at the results while the simulation is still going on. So some of the simulations that I'm running now, they'll take like a week or so. And so it's just kind of nice, especially since I'll initially, maybe I care mostly about this get cloud data, which was used to generate that mass growth plot shown on another slide. I also have another script which generates some slicer projection plots. And I think maybe what you're pointing out is, why don't I just have the simulation itself do some of this sort of post-processing really within the simulation? And the main reason for that is just there's always one additional analysis that I want to do. So it's just a little bit easier to do it in post-processing, since otherwise I'd have to keep on rerunning these simulations, and it's just a little bit easier for me to do it in post. But definitely it would be nicer. Definitely some of the analysis that I've thought up now, I thought, man, I wish I could have just done that during the Flash simulation initially. Yeah.
Okay, cool. Thanks very much.
Yeah, thank you.
Okay, I don't see any other hands up. Oh, Stephanie.
Hi. Really cool talk, Ryan. Thanks. So I was just wondering, one of my big problems is, just the fact that you could do anything with YT, more or less. And so when you had like those mass plots, have you thought about, right, that must, do those indeed include a like density threshold of gas?
Yeah. Yeah, good question. So the solid lines are showing density threshold of within 1/3 of the initial cloud density.
Mm-hmm.
And then the dashed lines are showing a threshold of has to be less than the geometric mean between the cloud and hot gas densities. So we're looking at two different things there, but yeah, there are a lot of different ways you could really just define what is the dense gas or what is the cold gas.
Yeah.
And I was doing that with cut regions, by the way. I agree that they're super nice.
Yeah. I think this work is really good, but I'm also kind of struggling with, this, what's the best kind of density threshold, or maybe you should be using a temperature threshold instead, really.
Yeah, so actually we've looked at temperature and density threshold. Since this is purely hydrodynamic, we find that we have like thermal equilibrium, or we have pressure equilibrium the whole time. So it's actually doing the same thing. But
right.
It's a really good point, especially if you have magnetic fields and you don't have thermal pressure equilibrium, then it could really matter.
Mm-hmm. Yeah, cool. Thanks. This is really interesting.
Yeah, thank you. Oh, and by the way, I don't know if I mentioned it, but the RAM pressure stripping work is work with Stephanie, and it's ongoing, but maybe see a paper in 2021 on it.
Yay.
Exciting. All right, so I think that we are now on to the discussion and lightning talks. I wasn't